happen. You see here, number one, so here we have, three sites. I mean, site one, we have a three process. So P1, P2, P3. P1 is waiting for P2 and P2 is waiting for P3. P3 is not waiting for anybody. So as a local site, you don't have any cyclic wait. So ultimately, this node or this site, they can go for the allocation of resources. The same way, when you come to site 2 also, you can see here, P4 is waiting for P5, P5 is waiting for P6, but P6 is not waiting for anybody. Forget about this line, what I've connected in the edges, okay? Leave that one. So P6 is not waiting for anybody. So again, within this site, there is no deadlock. Again, when you come back to site 3, here also you can understand there is no cycle, wait is forming. Again, the same way in site 4 also, there is no cycle forming. So ultimately, the individual site, they can check for the deadlock deduction, and ultimately there is no deadlock. Can you tell me when there is a deadlock in site 1 can happen? If P3 connected back to P1, yes or no? If P3 is waiting for P1, ultimately there is a cyclic wait and the site 1 will get into the deadlock. So that kind of a deduction within the local site, they can do it. They need not to do any probe or they need not to send any messages to anybody. They can do it as such. Are you getting my point? So each and every site, there is no connectivity as such. So they are not able to, there is no deadlock, within the site. Okay, what is the next point? Well, how we are going to connect? Now you see here, the last person in P3, so he is the one, is the edge node to connect with the another edge node on the another site. So P3 and P4, these are all the edge. Are you getting my point? So P3 is connecting with the P4 and P6 is connecting with the P7 and the P8 and P9 connected with the, is waiting for P10 and P12 is waiting for P1. So again, in a physical eyes, when you see this one, 100% we can say that there is a deadlock. But how the system is going to run, how the algorithm is going to detect whether there is going to be any, the deadlock scenario is going to occur or not. Okay, so this is one particular point you need to understand. Now, what they are going to do, come back to the point what I said. So they need to send a probe. What is a probe? I told you very clearly in the previous slide. The probe is nothing but, do you remember the probe which I told? The probe is nothing but what? The probe is nothing but IJK. Okay, IJK. What is IJK? IJK is nothing but I is the initiated, the PI, and the J is within the site, and the PK is the next node. So come back to this. What is the probe here? I is nothing but the first person, P1, he is initiating the deadlock deduction. Are you getting my point? P1, the PI is the number one person who is probing this one. So what is this probe you see here? The number one is P1. Okay, the P1 is requesting, initiating the deduction. So I is 1. What is J? J is nothing but the edge node which is going to connect to the next site. What is the next site? Is 4. You can see here I, J, and K. So these are the three parameters will come to this particular site. So from this site, what probe will be sent? You can see always the first I will be the site which initiates the deadlock deduction. So here the site who initiated is 1. And what is the edge node? J is 6 and K is 7. The next site edge node. And come back here from P9 to P10. What is the probe? Again, 1 is the initiator. 9 is the edge node from where you are coming, that is the J, and K is 10. And again here from P8 to P10, you can see here I is the initiator, 8 is J, and K is 10. And again from P10, P11, P12, now what is the probe value? I is J, I is 1, J is 12, and K is 1. And now how they are identifying whether there is a deadlock? You see here the I is equal to K. If I and K value, if they are equal, then they are going to define that there is going to be a cyclic wait and that was going to lead to the deadlock. Is it clear to you? Okay. So this is how, this, what you can say, the edge chasing algorithm is going to work. So it is the most important person in this algorithm is nothing but the prob, the I, J, K, the value of I and the value of J and value of K. So through the edge connectivity, and they are going to identify whether there is going to be a cycle. At the end of the cycle, they will, the end of the edge connectivity to the initiator, they are going to check the value of I and J. If I is equal to K, then they are going to say that there is going to be a deadlock. I hope you got the point.
Yes, sir.
You got it? Okay.
Yes, sir.
So this is how the edge chasing algorithm is going to work. Okay, edge chasing algorithm is going to work. Now let me go back and give you the algorithm. Okay. So this is the algorithm. So determine if a blocked process is a deadlock. Okay, the system executes the following algorithm. So if PI is locally depend on itself, okay, then declare a deadlock. What we said in the previous diagram, you remember, if there is a deadlock dependency, P1 waiting for P2, P2 is waiting for P3, and if P3 is waiting for P1, I can clearly say that there is a deadlock. Are you following? Okay. PI is locally dependent on itself. P1 is waiting for P2 and P2 is waiting for P3 and P3 is waiting for P1. Then immediately you can declare there is going to be a deadlock. Suppose if there is no deadlock, in our diagram you can see that one, there is no deadlock here. So what you have to do, the else condition is for all Pj and Pk. All Pj means what? Your Pj is in the site 1 is P3. What is the Pk in the site 2? P4 for our example. Okay, such that condition 1, you see here and condition. This is what the and I was explaining to you in the beginning. So Pi is locally dependent upon Pj. That we have understood. P1 is waiting for P2. P2 is waiting for P3, but P3 is not going for the cycle. So Pi is locally depending upon Pj. That is true. Yes or no? P1 is waiting for P2. P2 is waiting for P3. Okay, so Pi is locally dependent upon Pj. I'm sorry, Pj. That condition is true. Okay, condition 1 is true. Are you getting my point? Hello?
So, yes, sir.
Yes. So Pi is locally dependent upon Pj. And the next condition, Pj is waiting on Pk. So P3 is waiting for P4. Okay, P3 is waiting for P4. If you come back to the next one, P3 is waiting for P4. So this is the point what we are talking about. Then Pj and Pk are on different sides. So that is the next condition. P3 in site 1, P4 in site 2. So condition 3 also satisfied. Now, if all these three conditions is satisfied, then send the prob message, which is called I, J, K to the home site of Pk. So what is the home site of Pk? Pk home site, I'm sorry. The Pk home site is site 2. So you have to send the prob message I, J, K. Okay. So 1, 3, 4. So that message you need to pass it. Okay. So now on the receipt of prob I, J, K, the sites take the following action. Now what are the receiving site is going to do? I'm sorry. What are the receiving site is going to do? In this case, what site 2 is going to do? So that is what we are going to see. So if Pk is blocked, so that means if Pk is in something, using what you can say, the critical section, or it's not, the resource has been not assigned to, somebody. So in that case, if Pk is blocked and E condition, the condition E is dependent of Ki is false. So what do you mean by dependent of Ki? So the P3 is waiting for P4, but P4 is not, going for a cycle. Are you following what I'm saying? The condition is false. The dependent Ik is false because they are not blocked. Okay, they are open right now. And Pk has not replied to all the request of Pj. they should not, that means what, are you, I hope you are following what I'm saying. If already you have given the resource, ultimately you are not able to get connect with the edge. Are you following what I'm saying? That's the meaning. So if that is the condition, then what we are going to do, begin. Okay, if this condition is false, then we are, I mean true, all the three conditions are true, then if this is if this is not true, then we are going to come back, begin, dependent k of I is equal to true and k is equal to I, then declare that pi is deadlocked. Okay, so then we are moving all the messages towards the end. Then we are going to find out whether I is equal to k or k is equal to I, whatever the value we are defining. If these values are equal, that is what I told you here. They are checking I is equal to k. What do you mean by I? At the last end, when you are coming for this particular, the edge, you can see I value and the k value. If it is equal, then we are going to say there is going to be a deadlock. Okay. So this is, that is the next point, what we are able to see here in this algorithm. Otherwise, you can see here, then declare pi is a deadlock. Else we are going to see for all pm and pn such that pk is locally depend upon, pk is locally depend upon pm and pm is waiting for pn, and pm and pn are different sites. So within the sites we are going to start. Okay, so each site there is no cycle, and if there is no cycle formation, and we will come back to the the inverse of what is happening of the previous examples of A, B, and C. That's why I say A apostrophe and B single quotes and C apostrophe. Okay, so this is inverse of what we have done in the beginning, and now we are going to do for a local site. And in that case, what you are going to do, you are going to send the probe. You can see here I comma m comma n to the home site of Pn. So then successively you are going to check again and again whether the values or the probe value, whatever you are sending, whether they are going to get into a cyclic wait or not. Okay, so this is the algorithm for the edge chasing algorithm. Okay, so here if you see the analysis part, m into n minus 1 divided by 2 messages for m process. You can see that one, each side we have 3 process. Okay, so in our example we had 3 at n sites. So we had 4 sites, I believe. Okay, so if you see that one, m into n minus 1. So in a book also they have given the same example. So that's why they are referring the same thing here. Okay, m into n minus 1 divided by 2. Okay, so if you want to see the example, I will show you this. Page number 167, I believe. 167. I'll show you the diagram, not 167, 167. Okay, so this is the diagram they're talking about. Able to see that one? Hello?
Yes, sir.
Yeah.
Yes, sir.
So this is the diagram they're talking about. Okay. So there are m into n minus 1 divided by 2 messages. So there are m messages, m processes at n sites in the the book, whether it is right. Ultimately, this is right because the analysis. But if you see that one m process n minus 1, this is going to be divided by 2. So this is going to be the n number of what you can say the messages. What it's going to the take in the what you can say the time complexity of this one. And again, if you see that one, there is a 3-word message length. What do you mean by 3-word message length? This is I, J, and K. Okay, I, J, and K. So that is the very fixed message. We are not going to, and it is going to be an integer. Okay, it's going to be an integer. So it's always, in a network, it's, if you are sending a very, what you can say, the fixed integer value, it is always danger. Okay, it's always danger. So that's why in a RPC, if you remember what I have taught in the class, remote procedure call, there is what we call the concept called marshalling. Okay, the parameter passing cannot send it as like how you are sending in an individual program. Okay, in an individual program, when I send a parameter, how I used to send either by call by value or call by reference. It is easy. It is very much easy because no outsiders are going to come to read my parameter because the focus of my program is within my system. But when I take this parameter value to outside the network, I need to be very careful. So passing the integer and the fixed level of integer value, it's always is going to be a danger one. Okay, so that is another important point we need to understand here. And the third one is going to be, again, it's the same way, like our path pushing algorithm, the order of n is going to be the delay to detect the deadlock. Why? I'm not able to prove when I come to the site 2. Okay, I have to come back to the site 1 or the initiator from where I have started because my formula says k is equal to I. Then only I'm going to define whether there is going to be a deadlock and it's going to occur or not. So till that particular point of time, I'm not able to define whether there is going to be a deadlock or not. So that is ultimately it's going to be order of n delay to detect the deadlock condition. I hope you have understood. Do you have any question? Hello?
Yes, sir.
Have you got the point?
Yes, sir.
Okay. So what about others? Okay. Okay. So everybody got the point? Right. So this is all about, the edge chasing algorithm and path pushing algorithm. This is purely for, distributed deadlock detection algorithm. It is not like a completely centralized one where we have a, global site to, to record the local site status and finding out the WFG and defining whether there's going to be a deadlock or not. Okay, so these are the two algorithms. This very much